Alrighty guys, I just kind of wanted to recap and walk you through some of the math behind strength of materials. Some of the equations that we talked about, I'm going to introduce a new equation. Again, they're pretty simple equations. Sometimes figuring out what the equations mean can be a little bit complicated, but these are the types of things that engineers in the real world, especially civil engineers and other engineers that are dealing with materials whose strength is going to matter, these are the equations that they work with. So the first equation, we've talked about this one. It's my stress equation. So stress, again, I apply a force to a material, and material is experiencing stress. So stress is force divided by the area that I'm distributing that force over. So again, these are in the notes. Remember that little symbol is sigma. The other equation that we've worked with, well, I guess we haven't really worked with it too much, but we're going to start taking a look at it here this week, is the equation for strain. And so when I apply a stress to a material, the material starts to give way, it deforms in some way. And again, if I'm talking about just like a column under compression forces, the length of that column is going to change. If I'm applying compression forces, it's going to get squished together. If I'm applying tension forces, it's going to be stretched apart. Either way, the length is changing. And so the equation I'm going to use for that is epsilon, that's that little symbol here, equals the change in length over the original length. So this L is going to be my starting length. And this delta, this little triangle symbol here, in physics that typically just means a change. And so I'm going to call this my change in length. Again, that could be squishing something together to make it smaller, stretching it out to make it longer. Either way, that's a change in length. Now, these two guys are related to each other. If I apply more stress to my material, it's going to be under more strain. And the equation that relates stress to strain, it's stress is equal, I'm going to put a big E here, I'll tell you what that big E means here in a second, times this epsilon. And so this is an equation that relates stress to strain. It's a very simple linear equation. I mean, you could think of something like y equals mx plus b, but there's no b here. Here, strain is my y, strain is my x, stress is my y, and the slope of this little linear equation is this e here. So that would be what would correspond with m. And what this little e is something called the elasticity. And if you think about elasticity, think about a rubber band. A rubber band is something very elastic. This number here is kind of a measure of how stretchy my material is. And so this is a property of the material, and I can figure out what this elasticity is if I know what the stress and I know what the strain on my material are going to be. Now, sometimes the fancy name given for this number here is called Young's modulus. And so every material has an elasticity. It's got what's called a Young's modulus that corresponds to how stretchy that material is. So again, some very simple equations that let us solve a lot of problems dealing with the strength of materials. So I've got an example here I kind of want to walk through, similar to the examples you'll see in your homework. So let's do that. So I'd recommend having these equations written down somewhere in your engineering notebook. Make it a note of what these different variables mean. Some of them are obvious. F means force, A means area, but some of these Greek symbols you may or may not be familiar with. So here's the problem I got to go over. It says a cross-section of a 100-inch concrete I-beam is shown here. The compressive strength of this material is 3,250 pounds per square inch. We're going to answer some questions about this material. So the first question is asking about what the maximum compressive force that this beam can support. Then under this maximum load, that compression causes a slight change in the length of the material. Can we calculate the strain? And then can we figure out what the elasticity of this material is from those two values? So let's start with A. So it's asking about the maximum compressive force that this beam can support. And that's going back to our stress equation. So let me write out our stress equation. stress is equal to force divided by area. And now when I'm talking about the maximum force, so this is F max, I'm going to replace F by F max. At the maximum force, the stress on the material is actually the strength of the material. So that's what we call F sub C. So that's the compressive, the force that the material can withstand. And this is the actual force being applied to my material divided by the area. So most of the problems we've solved so far had pretty simple cross-sectional areas. Either you have like a rectangular area, which you do length times width, or for like a cylindrical column, you'd have a circular cross-section, so you have pi r squared for that. This is an I-beam. It's a very common type of beam used in a lot of building and engineering applications. Figuring out what this area is going to require just a little bit more work. Let me go ahead and kind of solve this equation a little bit, because we want to solve this equation for F max. That's the maximum force this can support, this beam can support. So if I multiply both sides by A, it's a pretty easy equation to solve. A cancels out, and I get my, let me just kind of flip these sides of the equation. F max is equal to FC, the strength of my material, times the cross-sectional area. So I'm trying to figure out what F max is. I know that the compressive strength of the material, that's a number that's given, 3,250 times, I need to figure out what my area is. So going back to this cross-section, it may look a little tricky to figure out, how much is inside this I-beam, how much material is inside it, but it's actually, break this down, I've got 1, 2, 3 rectangles. And so if I start with this rectangle on the top, I've got something that's telling me the length of that rectangle and the width of that rectangle. So that's what B and L is in our worksheets. And so this is pretty easy to figure what the area of this rectangle is. So 6 times 1, so that's length times width. This is going to be 6 square inches. And it looks like the I-beam down here matches that. So again, this is 6 square inches. And then I need to figure out the area of this center support. And it looks like that's 4 inches long, ½ an inch wide. And so again, doing length times width, 4 times 0.5 gives me an area of 2 inches. And so if I want to find the total area of this I-beam, all I've got to do is add together my different areas. So 6 plus 2 is 8. Plus 6 is 14. So my area here is 14, square inches. And so again, that's a number I can plug in here in my equation. So 3,250 pounds per square inch times 14 square inches. And that's going to give me the maximum weight that this particular cross-section can support. All right, if I plug that into my calculator, I'm going to get 45,500 pounds. So this pillar with this cross-section, with this particular strength of this material, can support this much weight. And so that's the maximum. That's the maximum force that this pillar can support. Now, obviously, if I apply a force, especially a compressive force, to some material, there's going to be some change in the length of that material. So that's, again, strain in this material. If this is concrete's pretty resistant to compressive force. We wouldn't expect concrete to compress much. If this were a sponge or a clay or something like that, we'd expect a lot of compression. So if I want to figure out the strain, that's what Part B is asking for me. Under this maximum load, this beam compresses. What's the strain on the material? And so my equation is epsilon equals delta L divided by L. So this is the change in length divided by my original length. And going back up here, this cross-section, this beam starts out at 100 inches, and it's compressed to 99 inches. And so the way I can figure this out, the change in length is going to be 100 inches minus 99 inches divided by my original length, which is 100 inches. and that's going to give me the strain on this material, which, again, you can plug that into your calculator, or that's a super easy thing to work out in your head. We 0.01. Thinking about the units, this is length divided by length. There's not actually any units that go along with the strain. So 0.01 is the strain of my material. And now we can use this to get an idea of how elastic my material is. Again, just going back to this new equation. So for part C, it's asking about the elasticity. So if I write that equation out, it says the stress of my material is the elasticity times the strain. And you can think about this. If I have a stretchy material, if I got a material that's got a high elasticity constant, the stress relative to the strain in the material is going to be a little bit less. Easy to figure out just by plugging in some numbers. At the maximum load applied to this beam, I'm dealing with my compressive strength, so this is going to be 3,250 pounds per square inch times this big E for my elasticity. And we figured out what the strain of this material is. It's just 0.01. And so again, this equation may be a little tricky to understand what it's talking about, but once I plug in numbers, this is a very simple equation to solve. I'm trying to solve for E. I've got times 0.01. All I got to do is divide both sides of this equation by 0.01. So those numbers cancel out. This divided by 0.01, you can plug that in your calculator, or you can do a little bit of mental math. You're going to get 3,250, and this is essentially adding 2 zeros on the end of that. So that's the elasticity of my material. So just a quick little sample problem, kind of going through the calculations, how we would work with some of these equations. Again, I've said this before, the equations themselves, figuring out what the symbols mean may be a little tricky. Actually, solving and working with the equations is pretty simple. So make sure you have these equations written down and try some problems on your own.